And in the last few years, during my postdoc, I've been measuring magnetic fields at distances very close to magnetic materials. So few nanometers to 100 nanometer distance, typically. And I got really quite amazed by what kind of information you can extract from those magnetic fields. So the first field you may think about when you measure the field of a magnet is the static field. So by imaging the static field, you may be able to say something about the magnetization, so the spin structure of the magnet. But if you go to somewhat higher frequencies, like gigahertz frequencies, those fields are actually very interesting. They contain a lot of information about material, and they are generated, we found out, by spin waves. Of course, otherwise I wouldn't be here, basically. So these fields are like generated by these spin waves. We try to pick up with a single spin sensor. This is a single spin in diamond that you can use to measure magnetic fields. And we developed some techniques to probe the spin wave spectrum in films, to probe the spin wave chemical potential in such films. So why are spin waves interesting? Well, I can identify basically 4 crude application areas. I think the biggest one is probably in spintronics. So there the dream is that you use the spin of the electron instead of its charge to transmit information, like it's depicted in here. And it's really a big field. There's a lot of things going on. So people are trying to make these kind of nano devices where you have a spin wave transistor, so you can generate some spin waves. You can turn on and off the channel, and you can detect them at a later stage. So there are some nice components being developed in this field. So a second field, which is much smaller, but I think is very interesting as well, is the field of quantum magnonics. So when you talk about quantum spin waves, you call them magnons. And here I show an extremely nice experiment that shows that a magnon is really a quantum particle. So what they did here in the group of Nakamura in Japan was they put a qubit into an electromagnetic cavity. So a qubit is a quantum 2-level system, so you can use it to create a single excitation. So they excite the qubit. That excitation decays into this electromagnetic mode in the cavity, and that mode excites a single magnon in this Yig ball. So you have one quantum of excitation in your qubit, goes into your single magnon in the Yig ball, and it goes back and forth. So you get coherent oscillations between these two systems. Now a third field I would like to identify is the field of nanoparticles. So mainly because it's just a very big research field, these nanoparticles are interesting for drug delivery in human bodies. So because you can manipulate them with magnetic fields, and maybe the spin wave resonances of these particles allow you to control the magnetization. And then finally, spin waves tell you something about the fundamental properties of magnets. So for instance, the spin wave spectrum of a magnet depends on the anisotropies in the system. So on the crystal anisotropies or on the shape anisotropies. So by measuring the spin wave spectrum, you can determine some kind of crystal anisotropies that the system has. And if you have a sensitive enough sensor, you can do so even in these kind of new materials, where it was recently published that van der Waals materials can be ferromagnetic. So these are monolayers just like graphene. And there was a recent publication that showed that these can actually be ferromagnetic. So these are some directions that we are generally interested in. And we have a sensor that is capable of detecting very small magnetic fields very close to a sample. So that would allow you to study, for instance, a single nanoparticle, to study the very weak magnetic fields generated by spin waves in magnetic monolayers, or to image the spin wave transport in these kind of devices. Now, what do we use to measure the magnetic fields of a spin wave? We use MV centers in diamond. So MV centers are defects in diamond. They consist of a nitrogen atom next to a vacancy in the diamond carbon lattice. There are a couple of electrons associated with this defect, and the 2 electrons basically make up a spin-1 system. So that's this orange arrow here. Now a spin reacts to magnetic fields because of the Zeeman effect. So here I plot the spin energy levels as a function of magnetic field for this spin-1 system. So you have 3 levels. And this is really the tool that we use to measure magnetic fields using the MV center. So there are a couple of techniques that we have to measure either DC magnetic fields or magnetic fields in the gigahertz range. And both of those techniques make use of what makes MV sensors really special. And what makes them really special is that you can initialize the MV spin just by shining a green laser at it. Then it will polarize into the 0 state. And then if you manage to flip it into one of the other states, the photoluminescence that it emits when you excite it with a green laser actually dips. So you have a spin-dependent photoluminescence which allows you to read out the spin. So for instance, if we want to we apply some magnetic field and we want to measure that field, what we do is we prepare the MV center in the 0 state, then we sweep a microwave signal over this resonance, and we monitor the photoluminescence. And then you can see that the photoluminescence dips as soon as you hit the resonance condition. And so from the frequency at which that occurs, you can infer the magnetic field. So this is a technique, we call it DC magnetometry. You can use it to measure DC magnetic fields, just measuring the Zeeman splitting of the NV center. Now in the second technique, this is what we use to characterize gigahertz fields. I will come back to this technique a lot in this talk, is where we measure the relaxation dynamics of the NV spin. So again, we prepare the spin in one of its three states, for instance in the MSS0 state, and then we monitor how long it takes before it decays into the other states. Now that decay rate here is directly proportional to the amount of magnetic field noise at the ESR frequency. So what we do in the measurement is we prepare the NV center, say MSS0 or MSS +1 or MSS -1, and then we measure the rate at which it goes into the other states because of relaxation. And for instance, in this measurement, you can see that this rate is slower, so the +1 rate is slower than the -1 rate. It tells us that there is little noise at this transition frequency and a lot of noise at this transition frequency. And actually, by fitting this data, you get a quantitative number, so you know the power spectral density of the magnetic field noise at the NV site. So this sets basically the stage for my talk. So in this talk, I will describe two techniques that we developed using NV centers as magnetometers to probe spin waves. One is concerned with confined spin wave resonances in magnetic microstructures, and the other is concerned with spin waves in planar magnetic films of YIG. And then in the second half, I will describe a technique that we recently developed, is that we use magnetic field measurements to actually extract the chemical potential of spin waves in the system. Now the chemical potential is an interesting spin transport quantity because it basically determines if, say, you have a high chemical potential at location A and a low chemical potential at location B, you will get spin wave transport from A to B. So it's a key parameter in spin transport. Now to measure these kind of very weak magnetic fields from a magnetic system that are generated by spin waves, you have to get extremely close. So for that, I would recommend you watch this movie, because these people really mastered the art. Up close and personal. So we developed 3 ways to get our NV centers up close and personal to our magnetic system of interest. So the first way is very simple. We take a diamond chip. It has NV centers implanted into it. We let them implant by a company. They're maybe 50 nanometers or 10 nanometers below the surface. And then you can deposit some magnetic structure of interest directly on top of the diamond. And now you can use your NV center to study the magnetic field generated by this magnetic disk. A second way we developed to get the NV center close is more useful when you cannot deposit your material directly on the diamond. So with permalloy, this is possible. It's a polycrystalline material that you can evaporate in the clean room. But for YIG, you typically grow it epitaxially on a lattice-match substrate. So it's hard to do that on diamond. So what we do then is we carve out these very small nanostructures of diamond that contain single NV centers, and we position them on top of the YIG. And in this way, we get a very close distance of maybe 100 or 200 nanometers. Now, the final way that was developed in our lab is a very flexible way to do, say, magnetic imaging. It's also the most technically challenging way. So we make these diamond cantilevers that have a very sharp pillar at the end, and at the very end of that tip there is a single NV center. And we mount this, we attach it to an atomic force microscope, and that allows us to scan this tip over a surface and make measurements with the NV center locally of that surface. So this is good for magnetic imaging, but today I will just focus on these somewhat simpler techniques up here. So the first technique I would like to show is how we detect spin wave resonances in these kind of magnetic microstructures. So here I show a permalloy disk that I deposited on top of a diamond. In the experiment, this was about 5 micron in size and 40 nanometers thick. And then we apply some magnetic field to magnetize the disk. Say that's in this direction. Say the magnetization will be in this direction. And then we try to detect the spin wave resonances of this disk. And we do so by applying a microwave drive field to the system, which is homogeneous in space. So we expect that we are very efficient in exciting the homogeneous resonance of this disk, which I will call the ferromagnetic resonance. So in the experiment, we do the following. So we apply this microwave drive field, and at a certain frequency, we hit the ferromagnetic resonance of the disk. This will cause the spins in the disk to precess, thereby reducing a little bit this projection on the equilibrium magnetization direction. So the magnetic field generated by the disk actually becomes a little bit less. And that's something that we can measure with our NV spin. So we just measure the change in the DC field of this disk as we excite a spin wave resonance. Maybe I'm a bit too far. So the measurement looks like this. So here I plot this change in the disk field as we sweep this microwave drive field as a function of a magnetic field. So you can see a very clear resonance. This is when we hit the ferromagnetic resonance of the disk. The disk field changes a little bit, and we pick it up, as you can see in this measurement. Now again, this disk contains many spin wave modes that are higher in energy, but in this measurement we don't excite those because our drive is spatially homogeneous. But I just would like to recall that above this bottom or ground mode, say, there's a continuum of spin waves that I will probe later in the measurement, in the talk. So let me then go to these new measurements. So we try to now detect these higher energy spin waves in the system. We do basically 2 experiments. One is where we don't drive the system at all. So we just look at the magnetic field noise that's coming out of the system without exciting it. And then we start driving the system, and then that story leads to this chemical potential detection. So we did these measurements on thermally excited spin waves on YIG and on permalloy. I will show you some YIG data today. And again, so to get our NV centers close, we deposited a diamond nanobeam on top of the YIG. In this case, this film was 20 nanometer thick. And then we have a gold and platinum strip line to drive the spin wave system. So the gold line we use for microwave excitation, and the platinum we use for spin injection via the spin Hall effect. Okay, so let me show you what happens when you measure the magnetic field emanating from such a magnetic film using an NV center. So to understand this measurement, I sketch here what I expect the spin wave density to be as a function of frequency and the magnetic field. So you can see here the bottom of the spin wave band described by the Kittel law. And then above that, you can see in this fading colors, there are some thermally excited spin waves, the density of which is described in principle by the Bose-Einstein distribution. But at room temperature, this just becomes the Rayleigh-Jeans distribution, which falls off as 1 over frequency. And I try to indicate that 1 over frequency dependence by these fading colors. So now recall that in the beginning I said that our NV center allows us to measure the magnetic field power spectral density at ESR frequencies. So by changing the magnetic field, we can change our detection frequency, and we basically have 2 detection frequencies at the same time. And what we can do in a measurement is characterize the relaxation dynamics of the NV center as a function of the field. It looks like this. So if I plot the relaxation rate corresponding to this transition, I get this blue curve. And if I plot the relaxation rate corresponding to this transition, I get the red curve. And you can see that it kind of qualitatively looks very much like what you expect, right? So if the blue curve is below the spin wave band, which is right here, then you get slow relaxation. But then as soon as you cross into the spin wave band, you get all this magnetic field noise that you pick up with your NV center, which is generated by spin waves. Now we can be more quantitative. So we write down the relaxation rate of the MV center in an equation, and it's a fairly simple equation with very few unknowns. So basically the relaxation rate is determined by the magnetic field noise generated by the spin waves in the system. So we just have to write down what is the spin wave density in our system and what magnetic fields does that density generate. So you can see here, this is this Bose-Einstein distribution in the high temperature limit, which is a kT over omega function. So this is some occupation function, which you multiply by a spectral density function, which describes the spin wave band. So we have a thermally occupied spin wave band here. And then we have to include this transfer function, which calculates which spin waves actually generate a field that we can pick up. So we don't probe magnetization directly, we probe magnetic fields. And for instance, the ferromagnetic resonance is a homogeneous mode. And in principle, such a homogeneous mode doesn't generate any field outside a film. Any homogeneously magnetized film doesn't generate a field outside the film, as long as it's infinite. So we are sensitive mainly to spin waves that have a wavelength that match the distance between the MV center and the film. If the spin wave has very fast wavelength, also that doesn't generate any field at our MV center. So that's all described in this transfer function, which we can know quite well and we can just write down. And then we know the spectral density as it is described by the spin wave dispersion of YIG. So in our case, it looks like this. For a 20 nanometer YIG film, it's a bit anisotropic because of dipolar interactions. So we plug that in, and then we use this equation to fit our data. And from this data, we can extract the distance. So that's the parameter D. So there's really not so much new physics here. We just extracted the distance of our MV center to the film based on magnetic noise measurements. But for us, this is a really nice measurement, mainly because it gives us confidence that we understand what's going on. Yeah. Yeah, so that's a good question. I didn't mention this parameter yet, but this is indeed chemical potential. And in this case, I'm not driving the system. So it's just in thermal equilibrium without driving, so it's 0 in this measurement. Yeah. And then later I will try driving the system, thereby increasing the chemical potential and extracting it from the measurement. Yeah. But in this case, it's a very clean measurement, so we're not driving the system, we're just looking at thermal excitations of the system, which are described by this Rayleigh-Jeans factor times this function that describes the spin wave band. So you can see that we get a nice fit, so it gives us confidence that this is the right description. So indeed, the magnetic noise is generated by spin waves in the band, and it's described well by this equation. Now we can go to a new situation in which we drive the system. So what we do here is we apply a microwave field with our on-chip gold strip line, and we measure the NV center photoluminescence. So that's in the color scale. Now the first lines you may recognize are these straight lines here. These have nothing to do with a magnet. They are just properties of the MV center itself. So these are these electron spin resonance frequencies of the MV center. The photoluminescence dips when you hit one of the ESR frequencies of the MV center. So that's what you see here. But on top of that, you also see this FMR mode, right? So it follows this kind of square root Kitolol behavior, which gives us confidence that it's the FMR. We can also calculate where the FMR should be for a film, and it's consistent with this line. Now, this effect that you see, so you just put your MV center on top of a YIG film, you drive the FMR, and you see that in the MV center luminescence is very peculiar. It was first seen by the group of Chris Hamill in Ohio State, and later it was found out what actually caused that effect, because in principle the MV center is not sensitive to magnetic fields that are generated by this homogeneous mode, like I described earlier. So why do we see a dip in the photoluminescence? Well, the only conclusion that we could make is that when we drive the FMR, we are actually exciting higher energy spin waves, some of which are resonant with our ESR frequency and cause NV spin relaxation. And that's how we pick it up. So we try to explore this mechanism in more detail. And we have the following picture with it now. So when we don't drive the system, the chemical potential is 0. We just have some thermally occupied spin wave band, and we get a certain relaxation rate of the MV center. But if we drive the MV center, we pump spin waves into the system, and we should see this relaxation rate of the MV center corresponding to this transition, which probes the spin wave density at this frequency, it should go up. So we would expect when we drive the FMR, we get more NV spin relaxation. Now, if this process increases the chemical potential of the system, we have a very simple way of extracting it. And we can go back to our equation to understand this. So here's the chemical potential, mu. So what we do is a very simple procedure. We measure the relaxation rate when mu is 0. So just the thermal spin waves are causing spin relaxation of the NV. The chemical potential is 0. We measure the density at these frequencies. Then we drive the system, increasing the chemical potential, and we do that. We again measure this gamma, but now at a finite mu. And then you can take the ratio of these two measurements, which are right here, and then all these details about the spin wave spectrum and things like that, they drop out, and you get a very simple equation for the chemical potential of the system. So here we measure the relaxation rate of the NV center as a function of the drive power at the FMR frequency. So we are driving the FMR, thereby creating higher energy spin waves, and we monitor the density of those higher energy spin waves at the ESR frequency using NV spin relaxometry, so by measuring this relaxation rate. So at 0 drive power, you may recognize this bump that I showed earlier, which is caused by thermally excited spin waves. And then as we increase the drive power, we see that the relaxation rate goes up. It means that we are creating spin waves in the system at NV ESR frequency. And remarkably, you can see that it saturates. Now we can use our equation to calculate the chemical potential. It also saturates. And the value at which it saturates is exactly at the ferromagnetic resonance frequency, which is, in our case, equal to the bottom of the spin wave band. So this is for us an extremely important measurement. The fact that it saturates at the bottom of the spin wave band is exactly what you would expect for a boson system. So it gives us confidence that we are extracting the chemical potential correctly. So again, to explain this a bit more, as we are increasing the chemical potential of the system, at some point we hit the bottom of the spin wave band and it kind of stops there. It doesn't want to go up more. If you drive the system harder, you get these peculiar effects like macroscopic occupation of this lowest energy mode or Bose-Einstein condensation, things like that. Ah, that's a good point. Yeah. Yeah, thank you for raising that. Yeah. So this equation will indeed saturate, as so that's well spotted. So as you can see, if this goes, say, to infinity, then this equation will saturate at h bar omega plus minus, which are the ESR frequencies, right? So, and what we see instead in our data is that it doesn't saturate at the ESR frequency, right? It saturates at the FMR. Yeah, so right, yeah, that's correct. So we assume that the chemical potential cannot increase beyond the bottom of the spin wave band. Yeah, yeah. What is important? Well, I mean, this saturation at the bottom of the spin wave band is not built into our equation, right? Built into our equation would be that it saturates at the ESR frequency. We have no reason a priori to expect that it would saturate at this value just from, so what we do is we measure relaxation rates, right, of the MV center. We use our equation to calculate the chemical potential and boom, it saturates exactly at the minimum of the spin wave band, which is, for us, a really remarkable fact, and it gives us very much confidence that this is the right interpretation of our data. So again, this bottom of the spin wave band is right here. Let me see how much time. Yeah. All right. So I have a few minutes left. So I would like to show you the last measurement that we did, injecting spin waves via the spin Hall effect in platinum. Oh no. So I first come to the great theory explanation. So sorry. I will. So what we did now is we analyzed this power dependence a little bit more. And try to understand, so what you can see here is this peculiar behavior that at low magnetic fields, the efficiency of this increase of the chemical potential is quite low at low field. It's very fast at high field, and then we go, as we drive it harder, into some other regime where we get say a nonlinear response of the system. But what we try to do now is we analyze this behavior. So why is this process of increasing the chemical potential inefficient at low field, but efficient at high field? So here I plot the low power regime. So this is the same data as in the previous slide, just a low power regime. You can see that this increase of the chemical potential is very slow at low field, and it's fast at high field. So if we plot those slopes in a graph, we get the following data. So you can see at low field the rate is slow, and at high fields the rate is very fast. Now why is this? And now we come to a very nice collaboration that we had with Prami Upadhyaya and Jaroslav Tverkovniak from UCLA. So they developed a theory that describes this kind of coupling between the FMR and the thermal spin wave bath. And we already heard about this yesterday in Benedetta's talk. So the coupling parameter is known as the thermomagnetic torque. And I will describe a little bit about this theory and then show how we can extract this coupling parameter. So in the theory, what happens, so the theory tries to describe that when you drive the FMR of the system, why do you create these higher energy spin wave modes? So when we drive the FMR of the system, our magnetization of the film starts rotating. So this is a bit of a complicated graph, but I will go through it a bit slowly. So here you can see the magnetization of our film. We apply an external field at an angle with respect to the film, so the magnetization is a little bit out of plane. Now we start driving it, the FMR will do this. So we have a precessing ferromagnetic resonance, and here a thermal magnon comes in, takes a little bit away of the angular momentum of this precession, and out come two thermal magnons. So this is the process by which we understand that we are populating this thermal spin wave bath and creating higher energy magnons. So the efficiency of this process depends critically on the angle of the magnetization with respect to the film. So in the theory, it was worked out that when the angle is 0, so when the magnetization lies in plane, the efficiency should be 0. But now as we start increasing the at low magnetic field, the magnetization lies in plane because of the demagnetizing field. This is a shape anisotropic effect. The magnetization likes to be in plane. But now as we start increasing the field at some angle, slowly the magnetization will start to turn out of plane, and at high field it will point along the field. And you can see that this efficiency increases. Yeah. 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 Yeah, so maybe I will give this to you. Yeah. So I think the question is, why does this efficiency grow with the angle of the magnetization as it tilts out of plane? You need to do some analysis of the underlying physics, right? Yeah. Right. So what we do to derive this curve is we write down this equation which describes the thermal magnon density, the rate of change of the thermal magnon density as a sum of two terms. So this is basically the damping into the lattice, and then this is this pumping term, where n is a vector that points in the same direction as the magnetization. So here you can see that this dynamics via this thermal magnetic torque increases the thermal spin wave density. And now to extract this coupling parameter, what we do is we average this equation over time, and we set this guy to 0 because we're in a steady state. And that averaging is indeed, you need to assume some adiabaticity condition. I would refer you to Jaroslav about this condition, because it indeed is it is a complicated aspect of the theory, I think. And so maybe Jaroslav, if you want to comment on how we average here, you're more than welcome.
Left open-ended. I mean, there are some aspects which we don't understand understand fully, but we kind of understand why we don't understand. Basically, there's some non-adiabatic effects. So the averaging, and it's discussed in the supplementary material. Experimentally, there's no what do you mean justification? No, it's not obvious.
Perhaps we can discuss this later.
Right. So I agree with you. It's a subtle point. But so what we do is we average this equation over time, and from that we can extract this thermomagnetic torque. And the nice thing is that this thermomagnetic torque, so it describes the coupling between the FMR and this thermal spin wave bath. And we find that it's about of the same order of magnitude as the Gilbert damping in the system. So that means that, for instance, when you drive the FMR, that it's significantly damped by this process of pumping thermal magnons into the bath. So finally, if I have some time. Okay, I will skip this slide. I would be happy to explain it later. So I would just like to give you an outlook. So this is an experiment I would be very interested in doing, where we use our techniques to study, spin currents and spin chemical potentials as a function of space. Here we would inject spins with some platinum injector and image basically what happens along such a simple spin wave nano device, which I call an interconnect. Okay, and I would like to leave you with my summary and thank you for your attention.
Okay, further questions? Yes.